engineering undergraduate student, and today I will be guiding you throughout the event from the start to the end. Okay, so without further ado, please give a big round of applause for Mr. Putu Suwarta and Professor Michael Robert Wisnom from University of Bristol.
Good afternoon, everyone. So it's nice to see your face here. And especially a lot of undergrad students, I think, and also Pak Ismail, who is interested to attend this lecture by Professor Michael Wisnom about the pseudo-ductile of carbon fiber composite. Hopefully from this lecture, we can adapt this technology to our own benefit, for creating more safe and efficient and also stable structure. So yeah, without further ado, I would like to give the spotlight to Professor Michael Wisnom. Thank you very much.
Thank you very much. And it's a pleasure to be here again to tell you a bit more about carbon fiber. So the work I'm going to talk about today is about thin-ply hybrid pseudo-ductile composites. And this was part of a large program we had in Bristol together with Imperial College in London on trying to create more gradual failure in composites. And this was something to which Dr. Putu also contributed. And I will show you some of the results that he contributed to this program as well. So, carbon fiber composites are great materials. They're stiff, they're strong, they're light. I spoke a bit about that last week. Great materials, but they do have a problem. And that when they do fail, it tends to be sudden and catastrophic, and they snap, and you don't get this gradual failure, this yielding and a ductile failure that you get with many metals. So the whole challenge of this hyperduct program was to see, can we add a metal-like ductility to these composite materials? And that was the goal of this high-performance ductile composites technology, or hyperduct program. So if you look at a typical metal, such as an aluminium alloy, you see aluminium alloy has a high strain to failure. Let me just get the pointer up. So this aluminium alloy, high strain, in this case here about 14%, and this yielding behavior. Whereas carbon fiber, it's stiff, it's got good strength, but when it fails at a relatively low strain and with a sudden failure. So what we wanted to do with this program was to create high-performance composites that show this same sort of ductile or pseudo-ductile response as what we see with metals. So we looked at various different ways of trying to achieve this ductility in composites, and the four main methods we looked at were first of all looking at fiber reorientation. So when you have angle plies, if the angle plies scissor, then you can get additional strain over and above the strain which is actually in the fibers, because the change in angle gives rise to a change in length, which produces additional strain. And so we had work on that, which was quite interesting. I'm not going to show you those results today, but you can see these nonlinear curves are a result of this change in angle. So this is a way of generating additional strain by reorienting the angles of the fibers. The second main way we looked at was by using strength dispersion. So rather than having one material which fails at the same strain, we have different materials which fail over a range of different strains. So one of the main ways of doing that was with these hybrid composites, whereby we use two different materials and we get this fragmentation. So that's what I'm going to be talking about today. We also looked at using discontinuous materials, where if you have discontinuous fibers, then you can have slip at the interfaces between the different materials, and this again can give you some non-linearity and a bit of pseudo-ductility. We didn't actually find that gave us a large amount of ductility, but it did produce a small change in the stress-strain response, as you can see on this curve here. So rather than just failing at this first point here, we've got a little bit extra with a bit of a plateau on the stress-strain curve. And then the fourth way was by creating ductile fibers. And at Imperial College, they did some very interesting work on using carbon nanotubes to make fibers which were truly ductile. So they had reversible, had a nonlinear behavior with a plateau and reversible true ductility. Whereas what I'm going to talk about today is pseudo-ductility, because there was some damage in the structure. But in the ductile fibers, they got up to 45% strain in a carbon fiber, which is very high strain, and it would then unload and you could reload it again. So in this presentation, I'm going to be talking about this strength dispersion via ply fragmentation in hybrids. So I'm going to talk about how we generate pseudoductility in these thin ply hybrids, and I'm going to talk about tension loading, which was how the first work was done. Then I'm going to talk about the fatigue response. I'm going to talk about what happens in compression and what happens in bending. So let's talk about pseudoductile hybrid composites, where we take... Okay, so we've got a okay, it's back again. We've got a high strain material, which might be a glass fiber composite, and we have a low strain material, which might be... Keeps turning itself off. I think that's a battery. Yeah, so in the example I'm going to talk about today, initially it'll be carbon and glass, but this is a general principle, and this could also apply to carbon and rami, for example, which might be a material you might be interested in investigating here. But any two materials where they have synergistic components. One is a high strain and a lower modulus. One is a low strain and higher modulus. Hybridize them together. And today I'm going to talk about hybridizing at the laminate level, different layers of the different materials, but you can also hybridize in other ways, which I'm not going to cover. If you do that in the right way, then you will generate a stress-strain response like that, which has got a plateau and some pseudoductility. But you do have to do that in the right way. You will not automatically get that sort of response just by combining two materials. If you combine them in the wrong proportions or with the wrong characteristics, you will not get that response. So in order to understand that, we have to understand what are the damage modes and how damage may develop in a hybrid composite. So there are at least 4 different ways. If we start off with this first one, if we have too much carbon versus the glass, then when the carbon fails, the load at that point there is immediately transferred on the glass, and there's not enough glass to carry the load. The glass immediately fails, and so you get a brittle failure at this point here. So it's not pseudoductile. So if we reduce the proportion of carbon, and we have less carbon to glass, then when the carbon breaks, there's enough glass to carry that load, so the glass does not break. But if we're not careful, what will happen is you get a delamination at that point. So the carbon will break, it will immediately delaminate, and you'll get a load drop. So again, it is not a gradual failure. However, if you make the carbon thinner as well, then there's not enough energy to propagate that delamination. And so when the carbon breaks, there is not enough energy to propagate the delamination, and so it just breaks at one point, and actually then you can get a break at another point, and you can get this progressive fragmentation. And it can either be like this, where the plies just fragment, or you can get a little bit of delamination locally, but not enough to join up and cause a complete load drop like we get here. And in these cases, with the thin plies and not too much carbon, then we can generate a plateau on the stress-strain curve and get this pseudoductility. So we did quite a lot of work analysing this, understanding how this works, and Mesam Jalalvand, who was one of the members of the research team, came up with these damage mode maps, where we try to understand how the different parameters which control the behaviour contribute to getting the response we want. So this is a damage mode map for S-glass and TR30, which is a standard modulus carbon fibre. And the behaviour depends on two things. It depends on the glass to carbon proportion, and it depends on the absolute thickness of the layer. So the proportion of glass and carbon affects whether it fails catastrophically due to fibre failure. If we have too much carbon, we get this premature failure of the whole laminate when the carbon breaks. But if we have less carbon, then we don't get that failure mode. On the other hand, if the plies are too thick, then when the carbon fails, we'll get delamination. But if the plies are thin and there's less energy, then we can get fragmentation or fragmentation with a little local delamination, and then we're in this gradual failure domain, and the colours here are indicating the expected pseudoductility. So the red here is the highest 0.15 millimeter glass plies, standard thickness glass plies, but these thin 0.03 millimeter carbon plies. And if we have 4 of these 0.03 millimeter carbon plies, so in other words here we've got, that's about 1 standard carbon fibre, you see we're in the delamination regime. And as we reduce the number of carbon plies, we get closer here. When we go to 2 carbon plies or 1 carbon ply, we're in this pseudoductile regime. So this particular one here is really quite interesting, because we can see from this prediction here that we get more pseudoductile strain, and we're some way from this barrier, so we expect to see a pseudoductile response at that point. And that's exactly what we found when we did these tests. So this shows the stress strain response of this case, where we have S-glass and then 2 thin TR30 standard modulus carbon S-glass, and you see we have a linear response, then we get this fragmentation, we get this plateau on the stress strain response, we get progressive fragmentation along here, and then when that becomes saturated, then we see an increase in the strain again. And what's interesting on this, in this case here, we've got 1.2% additional pseudoductile strain over and above what would happen if we just went up with the same straight line. This value here is the 1.2% extra pseudoductile strain. But as well as that pseudoductile strain, it's quite interesting the appearance of the specimen, because this specimen is black to start with because it's carbon, but when the carbon starts to break, then you get a little bit of delamination and you see these yellow patches appear. So I don't think you can see it on here, you might just be able to see it. In the middle of those yellow patches is a black line, and that is actually where the carbon fibre has broken. And so it's broken locally, a little bit of local delamination, which creates an interface, and because of the translucency of the glass, you can see it now becomes yellow. And then over here we have another fragmentation, and along the length we have these multiple carbon fragmentations, and between them it's still intact. And that's what gives us this plateau on the stress strain curve. So this is an example for glass and standard modulus carbon, but we can do the same thing with different grades of carbon. And this next plot shows 2 different types of carbon, where we're mixing a T1000, which is an intermediate modulus carbon, and XN80, which is a very high modulus carbon, and mixing those 2 different carbons together in this thin ply hybrid, where all the plies are quite thin. You see again a similar behavior with this plateau on the stress strain curve, a lower initial failure strain, because of this is a high modulus material, and again a plateau with about 1% pseudoductile strain there. So this is a very interesting response that we've been able to achieve by hybridizing these thin ply materials. Those results for unidirectional materials, we can't usually make use of carbon fiber in unidirectional form because there are typically loads in other directions. Even in a structure which is predominantly loaded in one direction, usually there's a certain amount of load in the other directions. If we have UD material, it's very weak across the plies, and it's a bit risky in most applications to have UD. Typically, composite materials are laminated with plies in different directions. So the next step was to look at the pseudoductile response in a laminate. So we hybridize carbon glass laminates, and there's two ways you can do the hybridization in this quasi-isotropic laminate. So quasi-isotropic laminate has the same stiffness in any direction, and that can be achieved by having 45, 90, minus 45 and 0 plies with the same thickness of each. There are other ways you can do that with a 0 plus or minus 60 or other combinations of angles. In this case, we're doing a 45, 90, minus 45, 0 layup, and you can do it in two ways. You can either take each sublaminate and put one carbon ply between two plies of glass at 45 degrees, do the same at 90 degrees, the same at minus 45 and the same at 0. And that one we call a material dispersed, where we have hybrid sublaminates that then are stacked at different angles to each other. Or the other way we can do it is we can create a hybridized, take a glass quasi-isotropic, a carbon quasi-isotropic, and a glass quasi-isotropic, and then sandwich those in this way here. So alternative way of doing it, this one we refer to as being orientation dispersed, and we've looked at both of these. They both produce a pseudoductile response, but this one tends to produce less issues with edge delamination. One of the interesting things with composites is that they can be susceptible to delamination from free edges, and by reducing the Poisson ratio mismatch, in this case here, we reduce the tendency to get edge delamination. So, showing you some results here. In this case, this is actually from a plus or minus 60 0 laminate, but again, it's S-glass and T300 standard modulus carbon. And you can see that we have a similar sort of response with a linear regime, a plateau on the stress strain curve, and then a further rising portion. And the failure modes are very similar to what we saw in the UD. We get fragmentation of the carbon plies, and we get some dispersed delamination, and that gives us this plateau on the stress strain curve. So the whole point of doing this is to try to achieve a more gradual failure. And the way we investigated this was to look at what happens when we put a stress concentration. So if you put a stress concentration, as I was talking about in my lecture on Thursday, composites are very susceptible to stress concentrations. If you put a hole or sharp notch in a composite, you typically see a big reduction in static strength. So by putting this pseudoductile mechanism in place, the idea was to try to reduce that notch sensitivity. And this shows the results of that same layup I've just shown, but this time with either a hole or a sharp crack in the layup. So the red response is the unnotched response, and the green and the black are showing notched response. And in both cases, the stress goes up to about the same level as it did in the unnotched case, and then it fails. So what you need to remember is that there's a stress concentration of about 3 around that hole, and so it's right down at this point here that actually the stress is reached at the edge of the hole, which could cause failure to occur. But it doesn't fail immediately, and as you go beyond that point there, all the way up here, we're getting progressive fragmentation around the hole, and that is redistributing the load around the hole in the same way as plasticity in a metal would distribute the stress around a hole in a metal sample with a stress concentration. And so at this point here, then by this point, we've got fragmentation across the whole specimen, and then it fails. So you can see this on these images here. You can see that we're getting actually, even down here, we've got got some fragmentation. It's perhaps not very obvious on this plot, but near the hole here, there's some fragmentation has started, then it grows across the width, and as you get nearer the failure, and then when you get to this point here, it's fragmented across the whole of the specimen, and at that point it does fail. And we get similar response whether there's a hole or a sharper notch there. So it successfully has reduced the notch sensitivity. So some work that Dr. Putu did on this was to look at the effect in fatigue. So this is all I've been talking about was on static analysis, but we also did this work on fatigue, where we took a similar material, S-glass composite with TC35, a different fibre, but essentially a very similar standard modulus carbon fibre with thin plies, and 2 of these thin plies between glass, and these specimens were tabbed and then loaded in tension. So the first thing to do here is to establish the behavior statically. So this was loaded statically, and we got a knee point strain and a plateau on the stress strain curve, and this point here, where that plateau starts, is referred to as the knee point stress. So the knee point stress was established by fitting these lines here, and then the specimens were loaded in fatigue under load control at a frequency of 2 Hertz, and they were fatigued below this level. So the fatigued up at multiple cycles at less than this knee point strain. And they were fatigued at a ratio of minimum to maximum strain, an R ratio of 0.1. So initially, when they were fatigued at 80% of the knee point strain, there was no damage. So 100,000 cycles at 80% of that knee point strain, no failure of the carbon, no damage at all. Then the load was increased up to 90% of the knee point strain, and initially there's no visible damage or change in stiffness until after about 30,000 cycles. Then we start to see in some specimens a reduction in stiffness, and this one here, it goes right up to about 100,000 before we see a significant drop in stiffness. So what's happening here is because 90% of that knee point strain, we're getting quite close to the carbon failure stress. Some of the fibers were already broken, and when we cycle it in fatigue, then you can get some damage growing. But not initially, so it goes up to quite a large number of cycles before that damage starts, and then it fails progressively. This red line here is the contribution without the carbon. So if you just took the glass without the carbon, you'd expect it to be about 70% of the stiffness of the original laminate, and you can see it drops down actually a little bit below that level, and that's because there's some splitting of the glass which also affects the load carrying response. But essentially at this point here, you're losing the contribution of the carbon. Well, what happens if we overload the specimens? So you can imagine a situation where we go beyond that knee point straight in static loading, in which case, in this case here, you can see, because we've gone past that point here, we've already got multiple fragmentations. So this has been overloaded past the knee point. What happens if we fatigue it now? Because now we've got some damage, and that damage may grow. So this is something which we can see in this slide here, that when it was fatigued at 80% of the knee point strain, after already exceeding that knee point strain in the first cycle, then you can see that this is what it looks like at the start. And after 5,000 cycles, it's delaminated quite a lot. And we can see it, there's been a lot of the specimen is now delaminated. And then after this point here, then we've already got fully delaminated the material. So if you look here, you'll see that there's a reduction in the stiffness due to this fatigue, but depending on the load level, it's quite slow. So these ones here, at 70% of the knee point, it's going up to about 10,000 cycles before it starts to drop, and it's going up to about 30,000 before it reaches the full delamination stage. If we do it at 80%, then it goes quicker, or at 90%, it goes after just a few thousand cycles. So overall, I think that's quite a good response, because these materials, we would not want to operate them above the knee point strain. So the design strains would be below that knee point, and so occasionally, if you've got an overload event, which is one of the things that we would want these materials for, to be able to cope with that overload event, you can overload it and still cycle it at quite high stress levels and not see an immediate delamination. So I think that shows that these materials are quite good from fatigue, and that's a very positive aspect. So what about compression? So when we first looked at this mechanism, we expected it mainly to give us a pseudo-ductility in tension, but it wasn't really very obvious what would happen in compression. In fact, we did not initially expect to see pseudo-ductility in compression, but we did investigate that, and this shows some of the initial work which we did to look at that. So in this case here, we've got a bending sample, and in that bending sample, we put a hybrid layer of glass, carbon, and glass near the compression surface of the bending. So this is a 2.7 millimeter glass epoxy beam with a hybrid high modulus M55J carbon fiber near the surface of the glass. And the way this was done was to measure the curvature on the edge of the specimen, and then from the curvature you can infer the strains, and you can work out the strains and see how that varies with load. So the 4-point bending results here show that at 0.5% strain, which is the failure strain of those M55 fibers in compression, at 0.5% strain, we see a change in slope. So that's what's happening. Do I need to do something? Is it a problem with my computer, or is it something at the other end?
It's trying to fix it.
Okay, we're back again, right. So, yeah, so we see this change in slope, which is associated with some damage, something's going on there. Initially, perhaps wasn't very clear what was going on there, but there's a definite change in slope at 0.5% strain. So to investigate that, this specimen setup was done, whereby we have a very small specimen here in this loading frame, which can be loaded up manually and then put inside the microscope to look at what's actually happening in the specimen during this behavior. And this has proved to be very interesting. Well, what you can see first of all is the top view of the specimen. We see these same sort of yellow lines that we saw in tension. So that's indicative of some local delamination around the fractures. And if you look on the edge of the specimen, then you can see there are these fractures occurring at regular spacing along the specimen, very similar to what we saw in tension. So what's happening is that the carbon fibers are breaking in compression, and there's a little bit of local delamination occurring there, which we can see through that yellow marks on the surface, and that's producing a little bit of additional local strain, a bit of pseudo-ductile strain, and is giving us that change in slope that we saw on that previous stress-strain curve. So one of the interesting things is to look at the spacing of those cracks. So this is a histogram of the fragment lengths along the length of that M55 specimen. And there's a histogram there, and you can see that of the order of about 0.5 millimeter plus or minus a bit. Now, in composite theory, there's something called the ineffective length, which is a concept for tension loading, that if you have a composite and the fibers break in tension, then there's a certain length of that carbon fiber which becomes unloaded. And you can apply that also at the level of ply. If you have a ply in a composite, a carbon ply between glass, and loaded in tension, then it takes a certain distance to re-establish the load in that carbon fiber ply as you go away from the fracture. And that's referred to as the ineffective length. And the critical length is related to the modulus of the carbon fiber, the strain to failure, and the thickness divided by the shear strength of the epoxy. Because it's the distance it takes to reload the fiber through shear at the interface as you go away from the fracture. And if you do that calculation for this set of materials, you find the critical length is 1 millimeter. So what that would mean is, in tension, you would not be able to get cracks closer than 1 millimeter. Because once you get to a 1 millimeter fragment spacing, then you can't get enough additional load into the fibers to break it. But here we're seeing that the fragment length is substantially less than this 1 millimeter. And the reason for that is because in compression, when the carbon fibers break, they're still carrying load. In tension, we break the fibers, that's it, there's no load carried across the fibers. But in compression, the fibers are still in contact, and although they're broken, they can still transfer some load. And you can see that in some of the microscopy of these specimens, that if you look at this one here, you see there's a crack in this M55 ply at about 45 degrees, and there's some local delamination. So this is with no load, so it's been loaded up and then unloaded, and this is what it looks like. But if you reload it again up to 1.2% strain, you can see that that delamination has opened up a little bit. So there's a delamination here which opens up under load, and that's what gives you this appearance on the surface where you see these yellow patches, because you have this localized delamination. But the plies are very thin, so that delamination does not propagate. And some very nice images here under the microscope, which shows what's happening. If you look, so this is the unloaded specimen after it's been initially loaded, then unloaded, and this is reloaded up to 1.2% strain. So if you look at this bottom area here, you can see that these fibers here there's a break in the fiber, so these yellow parts here are individual carbon fibers. So in this case here we've got about 3 fibers through this ply. So you can see the individual carbon fibers are broken at an angle, and this angle actually goes through the whole of the specimen. But if you look at this place here, you'll see that these fragments are roughly in line. But if you come over here, you see that they're actually slightly displaced sideways. Because of the angled crack under compression, there's a wedging action which opens up the crack. And this, you can see this better on this schematic. So here we've got the glass, the carbon between the glass plies. The carbon fiber ply has failed with multiple failures at an angle, roughly 45 degrees in many cases. And then there's a wedging action which causes some local delamination to occur there. And this produces some additional strain, which is what gives us this pseudo-ductility in compression. But if we load it too far, then this delamination may propagate. But because these plies are thin, then that propagation does not occur initially. So that's the schematic of the failure mechanism, and some very interesting results which Dr. Putu did on compression of these specimens here. The same M55J carbon fiber and S-glass with this thin 2 layers of M55, or different numbers of M55 plies between the glass, and multiple layers through the thickness, so 17 repeats of this sublaminate, because we need quite a thick specimen to load it in compression. And the number of carbon fibers together was varied between 1, 2, and 3. So these specimens are between 3 or 4 millimeters thick. They were tested in this Imperial College fixture, which is one of the better ways of testing compression. Compression testing is extremely difficult with composites because there's a risk of buckling. It's very difficult to get the load in without introducing shear and other failure modes. So it's very difficult. this is probably the best method of doing direct compression tests. And these specimens had a DIC pattern to measure the strain, and then they were loaded in compression. So this shows a typical response for 3 different specimens with 1, 2, and 3 plies. And the ones with 1 or 2 plies show this knee point in the stress strain response, and then they go to a much higher strain before eventually failing by delamination. But the one with 3 carbon fibers together in red, it just gets up to this 0.5% strain, and then when the carbon fibers fail, because you've got a thicker block of carbon, at that point you get a full delamination. So it fails immediately at that point because the carbon is too thick. There's enough energy to propagate a delamination immediately. But if you look at what happens, for example, with the single ply case, then we have fragmentation occurring here. So that gives us the change in slope, quite a significant change in slope because we've only got 1 thin carbon to every glass ply. But then it goes quite a lot further before we get delamination. First on one side, you can see that surface ply has delaminated. Then at a higher strain, the other side goes, and we get this one delaminating here. And then at even higher strain, the whole thing fails catastrophically. So that's what happens in a direct compression. Now what happens in bending? So bending is really interesting because we have tension and compression. One side of the specimen is in tension, one's in compression. We've looked at the pseudoductile behavior both in tension and compression, but in a bending test we'll get both of them. So that makes the behavior quite interesting. So the S-class M55 tested in bending with this laminate where we have M55 glass repeated through the thickness, and we've got here either 1 or 2 plies of M55 together, loaded in bending in the same 4-point bending rig. And this shows the results, which I think is very interesting. So let's just look first of all at let's look at the single ply case. So this is the green one. So initially it loads up, and this is showing the strains on the compression side and the strains on the tension side as we increase the load. You see that at about 0.5% strain we get fragmentation in compression. And so there's it's not very noticeable, but there's a bit of a change in slope occurs at this point here at about 0.5% because it's fragmenting in compression. Then we go higher, and at this point here, at about 1% in tension, then it starts to fragment in tension. So now we see much more change in the slope and more damage because it's fragmenting in tension as well as the compression that we saw down here. And eventually we get up to quite a high strain here and we get a catastrophic delamination. So we're seeing fragmentation first in compression, then fragmentation in tension, and then delamination. And I think this is a very interesting behavior, and we've been working this week on writing up a paper on this because I think it's really interesting and something which has not previously been seen. And if you look at the micrographs, you can also see how different the damage is on the tension and the compression side. So on the tension side, we see these breaks in the fibers which are perpendicular to the fiber direction. Whereas on the compression side, we see what look like shear cracks through the fibers at an angle of about 45 degrees. Now these look like shear cracks, but actually this is not what's happening. So I really prefer to call them shear-like cracks rather than shear cracks, because what actually turns out to be the case is that these fibers are actually failing due to an instability within the graphite planes of the fiber itself. So there's an instability at the microscale, even in a single carbon fiber, and we've done some very recent work, which is not published yet, where we've been actually able to see these microbuckles within single carbon fibers. So it's actually an instability within the fiber, and it gives rise to what looks like a shear fracture at a characteristic angle, about 45 degrees, but very different behavior in compression and in tension. Now that's for the M55 fibers. The M55 fibers, we find they fragment both in compression and in tension. But if we look at the TC35, which is a standard modulus carbon, then actually this behaves a bit differently. So the TC35, which is a similar hybrid we've got here, single ply of glass, TC35, either 1 or 2 plies, sandwiched between the glass, multiple plies through the thickness, loaded in 4-point bending. And this case, we only see fragmentation in tension. No fragmentation in compression, because this fibre has got a much higher compressive failure strain than the M55. In fact, the compressive strain to failure is higher in compression than it is in tension. And so what we see is we see a similar behavior in tension with fragmentation, and then it goes beyond that knee point strain, and then we get final failure. So what's interesting here is that with the 2-ply case is stiffer, as you'd expect, with 2 plies of carbon, stiffer than with 1 ply of carbon. We see in both cases, we see this fragmentation in tension, but there's a noticeable difference in the final failure strain. And in fact, the final failure occurs in compression. So it fragments in tension, and then we get a failure in compression, and the strain actually is different in the 2 cases. So for the single carbon fibre, it goes up to 3%, which is a very high strain for a carbon fibre composite. 3% strain at which we get catastrophic failure, but only 2.6% when we have a double carbon fibre. So this is showing a sort of hybrid effect. A hybrid effect is a term where we see one material goes to a higher stress or strain when hybridized with another material than it does on its own. And this case here, it's because the failure is controlled by instability, and when we have less carbon or more glass, then we have more support to those carbon fibers against an instability failure. So we see a change in the failure strain as we change the ratio of carbon to glass. So this is because the compressive failure is not a strength-dominated failure. We're not reaching a critical failure stress. What we're doing is we're reaching an instability, and instability is really a structural phenomenon, and it depends on the boundary conditions, on the support available to the different materials. So the previous results still showed us a catastrophic failure. So we got fragmentation, but still both the layups I showed finally failed with a catastrophic failure in compression. So we wanted to see how we could overcome that, and one of the ideas was to make a hybrid where we had glass on the compression and a fragmenting carbon hybrid on the tension side. So the idea here was to stop the compressive failure and activate the gradual failure in the carbon and see whether we could overcome this catastrophic failure. So by doing this, when the carbon starts to fragment, we get a shift in the neutral axis, and this allows gradual failure on the tension side without failing the specimen in compression. So to do that, we had a block of S-glass. This is unidirectional material, block of S-glass, and then this carbon hybrid, where we're hybridizing T1000 intermediate modulus with a high modulus M55 all the way through the thickness there. And these are all thin plies with a standard S-glass on the compression surface. And when we tested these, it behaved very well. So what we saw was fragmentation of the M55 on the tension side, change in slope, and then eventually we get to the point of failing the first T1000 on the tension side, get a bit of a load drop, go a bit further, fail the next T1000, bit of a load drop, and we get multiple failures with the T1000 through the thickness, followed by local delamination. And gradual failure and gradual drop in the load all the way down to this point here. And if you look at the specimen under load, then it's bent double and actually slipped between the loading rollers, but this specimen is still intact. It's not broken. So these fragments on the tension side are broken off, and when you unload it, it goes back like this. You can see you've still got glass and some carbon which is intact on the surface here, and all these spears of the carbon fibers which have failed on the tension side are just left like a brush type failure. So got a very gradual response there, and the specimen actually is unbroken, is intact, can still carry load if we want to load it up again. Did a similar thing with the quasi-isotropic layup, whereby now we have a 0 plus or minus 60 layup, glass on the surface, and carbon on the tension side. And again, this behaved very well. We got gradual failure, gradual fragmentation, the M55, and then progressive load drops on the tension side. So this gave us a similar mechanism of gradual failure as we saw on the UD, and potentially a very good energy absorption, for example, in the case of dealing with impact. And even after all this, the specimen is still intact and able to take some load. It's not completely failed. So that's a summary of what we found on the behavior of these materials in tension, bending, tension, compression, and bending. Just a few comments on the benefits of ductility and pseudoductility. This pseudoductility gives a warning that the specimen has been overloaded and might be close to impending failure. We get a non-catastrophic damage, but we get a detectable stiffness change. And in fact, that stiffness change can be seen visually in some cases. If we have a carbon glass, we can see it visually as well as measuring it by the change in stiffness. And recently, we've been doing some work on looking at the effect of electrical resistance. We can also detect the damage by a change in electrical resistance. So these composites then have the ability to still carry load after that failure initiation until the structure can be repaired or replaced. We've also got the potential to exploit a greater proportion of the fiber's ultimate strain. I didn't really talk about that, but actually this, by putting the hybrids together, we can actually achieve a higher strain than we could on their own. We do see some hybrid effect in both tension and compression, which means we can take greater advantage of the properties of the material. We also see load distribution around stress concentrations, which provides notch-in sensitivity, which is very good for avoiding failure from sharp cracks or holes or other stress concentrations. And potentially these materials should be less defect sensitive. Currently, if you look at the stress-strain response, carbon fiber composites are very limited. We've got materials which can go to about 2% failure strain, but typical design strains are more like about 0.4% strain. Our idea is that we can go beyond that and get closer to this knee point. We wouldn't want to operate above this knee point, but you could get much closer to that knee point and hopefully push that design strain further up. And also get greater energy absorption. And one of the things we've been doing recently is looking at using these hybrid materials for trying to improve the penetration resistance of casings for aero engines. So in conclusion, ply fragmentation can create ductility and notch-in sensitivity and tension. We see good fatigue performance with no damage at 80% of the knee point strain even after 100,000 cycles. And even specimens which had been statically overloaded, they only delaminate quite slowly over a few thousand cycles. We also see fragmentation and non-linearity in the M55 carbon in compression, and we see a gradual failure also in bending. The surface glass can eliminate the compressive failure and give us a very high energy absorption. So overall, I would say that these fragmenting hybrids are very promising as a way of avoiding catastrophic failure and providing warning and increased margin of safety. So there's lots of published papers on this work, which are included there, and very happy to take questions. Thank you very much.
Thank you very much, Michael, for the very insightful presentation. And this work, I've been involved during my PhD study for 4 years, and still continuing up until today. Me and Professor Michael we discussed about this paper about bending, the failure in bending. So Professor Michael talks about gradual failure. I would like to start. Why why do we start with gradual failure? Why not preventing failure at all? Why gradual failure? So
Well,
then we can start with discussing.
well, that would be the holy grail if we could prevent failure at all. But that's
please-
pretty challenging.
Yeah.
Sorry.
Can you put your mic?
Is it? Okay. Yeah, that would be great if we had materials that didn't fail. Actually, there is one which has been invented in the UK. It's called unobtainium. Yeah, that's not something we've been directly involved with. Clearly, there's a lot of, over the years, there's been a lot of effort to develop carbon fibers which are stronger. So if you go back to the original carbon fibers we developed back in the 60s, they were much less strong than the materials we have today. And the development has slowed in recent years, but we still now have T1200. So T1000 I mentioned there, then there was a T1100, there is now, I believe, a T1200. So there have been some developments in fibers which become stronger and stronger. But there are always trade-offs as well. And you reach limits, and there are other barriers, cost being one of them. But in this work here, I'm working in an engineering department rather than a materials science department, and what we're interested in is how can we use existing materials better. So there is work going on to improve the fibers, and I mentioned very briefly at the beginning the ductile fibers which Imperial College have been developing. So arguably those are fibers which could give us a better response. But in this project, what we were mainly concerned with, how can we take the existing materials which we have access to and which we can buy commercially, and how can we get a better response, given that one of the concerns about using these materials is this catastrophic failure. People don't like it. I showed a picture about the bicycle at the beginning. A lot of people are nervous about riding bicycles made of carbon fiber because when they do break, they go very suddenly and catastrophically. There have been quite a few nasty accidents due to that. Whereas if you have a metal, then it does behave much more with a much more gradual failure. And one of the applications we looked at was a carbon fiber hybrid handlebar, which did exhibit the same gradual failure that we've seen in these simple test specimens. And I would much rather ride a bicycle with a handlebar like that rather than one which fails like the pictures I showed at the beginning, where we can get catastrophic failure. So it's really about making the best use of the materials that we have and trying to engineer them to get a response which is better for the application.
Thank you, Michael. If there's any question or would you like to discuss, you are more than welcome.
Test. Okay. Good afternoon. Thank you for the opportunity. Professor Michael, there's something I would like to ask. Regarding stress concentration around open holes and notches, like previously shown on your testing, I am curious about how the hole or notch is introduced in testing without generating additional residual stresses or machining-induced damage, since this could affect the measured reading and the data we gather later.
So that machining was done in a fairly straightforward way with a fairly standard drill. So you do have to be careful how you drill carbon fiber because it is easy to introduce a lot of damage. It needs good back support. So normally would do it with a back support. Often we'd use wood on the back so that we don't, when you go through it, it doesn't introduce a lot of delamination. There's a lot of work been done, not by us, but there has been a lot of work published on how to do the machining. So that's relatively, if you're careful with the machining, you can avoid a lot of damage. Although in this case, arguably, it perhaps wouldn't be so critical if we had a bit of damage. And you were asking about residual stresses, were you?
Yes.
Residual stresses. So residual stresses are present. So residual stresses are present in any composite just because of the differences in the fiber and the matrix properties, and if you have multiple directional laminates, the differences in expansion coefficient. So all composites have some level of residual stresses. In a hybrid, you've got an additional level because the glass and the carbon, for example, have got different expansion coefficients. So that does have to be taken into account. So residual stresses are relatively small. So in the carbon glass hybrids I was showing today, from memory, I think we have of the order of 0.03% residual strain. So I showed failures in carbon at about 0.5%, and when we compare those, we need to account for the residual strain as well. So it's there. It's relatively small compared to the strains in the fibers. And with regard to the whole, then that's quite a tricky question, because you're not, it's a bit different from what happens in a metal. In the composite, the main issue really with residual stresses can be associated with the free edge. So you're removing a bit of material, but you're not really changing the residual stress distribution. So you're removing a bit of material, you're creating a new free edge, and so there will be some high stresses at that free edge, including some high residual stresses. But it's not really a problem because the residual stresses are relatively low compared to the failure stresses in the material. So I'm not sure whether you had a particular interest in these residual stresses, but overall I would say it's not such a big problem in these composites as it is perhaps in some other materials. We have done some work. I had some colleagues who, well, we actually have a spin-out company from the University of Bristol which looks at residual stresses in metals by drilling holes. So you drill a hole and then you see what happens to the stresses around the hole. We have tried to apply that to composites. It's very complicated because you have these free edge stresses, which makes it really quite tricky. But overall, I would say that residual stresses are probably not quite such a problem in this case. But if you have a further interest or question about that, I'd be happy to pursue it further.
Thank you for your explanation, Professor Michael. Because previously my concern is when working with more brittle polymer like epoxy, I'm afraid when drilling it will crack the epoxy before the hole is initiated properly.
Yeah, well, I think that could occur. But in the composite, we're not really looking for the epoxy is important to some extent, but cracks in the epoxy don't immediately lead to failure of the composite. So the composite is a bit more damage tolerant because most of the load is carried by the fibers. But certainly there is a risk of damage, and if you look in detail, not actually something we've done, but if you look in detail around the hole, you probably will find a bit of damage around the hole, but I don't think it's going to make such a big difference to the overall response of the specimen.
Thank you for your response, Professor Michael.
If you have any more questions or discussion you would like to conduct, or a question from the online participants maybe, if there's questions, or okay.
Hi, good afternoon. Thank you for the opportunity. So I was here on Thursday for your guest lecture, and for now I actually have a question regarding this in comparison to a regular carbon fiber. So usually with a material, there's a certain drawback that they have. Like for a normal carbon fiber, it's very brittle, and that's what you're trying to fix here with the pseudo-ductile material of carbon. So I was wondering, are there any compromises that you have to make in order to get that ductility or that pseudo-ductility on the glass carbon fiber composites compared to a regular carbon fiber? And when is it more preferred to use a normal carbon fiber compared to the glass carbon composites?
So there are trade-offs. You unfortunately in this world you rarely get something for nothing. So if you look at this response here, this stress-strain response. If you had a carbon on its own, it would go to a higher stress than this, but it would fail catastrophically. So it all depends what you want. If you're after ultimate strength, then you're better off with carbon on its own. But if you want to make it more tolerant of damage and to have this gradual failure and not see a catastrophic failure and to see more tolerance of notches, then this is a better response. So we've looked at different applications. Things like pressure vessels for storing carbon, they're really designed on ultimate strength and would not benefit from this because we're actually not exploiting the full strain of the carbon. But if you look on aircraft structures, then they're never designed up to the full strength of the carbon fibers because one of the largest concerns is notches. In aircraft structure, you have many notches, and so they're designed to notch strength, and particularly under hot, wet conditions where carbon composites can be very susceptible to damage. So in that case there, that's why this failure strain is only about 0.4, which is 4 or 5 times less than the strain that the material can really take. That's what a typical design strain. So in this case here, the idea is that we could maybe go a bit beyond that by making it less susceptible to damage or to notches. So it depends on the application. Ultimate strength, the carbon fiber on its own, but if you want a more gradual response, less notch sensitivity, then these hybrids can be an advantage.
Okay, thank you for your answer.
Any more questions? You're welcome. I hope you are not fatigued yet. I hope you are not fatigued, so it's not midnight yet. Or maybe some questions from the online participants.
Well, perhaps I've got some questions for you, or throw out some ideas. I mentioned during the presentation about using natural fibers, RAMI composites. So I think it's interesting. One of the things I find hybrid composites very interesting because you're combining different materials to try to improve the overall response. So what about other materials which might be available or of interest here, and how could they perhaps be combined to produce a better response? So perhaps carbon could be used to improve RAMI. Perhaps there are other natural fibers which could be put together and used together, 2 different natural fibers. Are there other ideas that you think might be relevant to apply this sort of concept of hybridization to get a better response in a different way? Not necessarily for gradual failure. It could be in other ways. How can we get the benefit by combining different materials? Any thoughts, ideas, opportunities there?
Yeah, any of you guys have been working with structure and material and combining different materials? Okay. So, may you introduce your name first, please?
Oh, yes. My name is Iverson. I am one of Mr. Puto's student in his polymer and composite class. I have a little thoughts about how we can improve to reduce the sudden failure, as we previously mentioned. I am currently working on natural composites, specifically coir, and I found that coir has it's very good at elongating before failure, although I'm not sure how good it is compared to carbon. But I think it's a good idea to implement coir as natural fiber to help preventing sudden failure.
Yeah, so coir I think is a good fiber. I'm not working with these natural materials myself, but I've seen quite a few papers published on many different fibers, and they all have their interesting aspects, and I think there's a lot more work needed. Natural fibers are actually, in some respects, more difficult to work with because you have natural variability, which can be a bit of a difficulty experimentally. But I think there's lots of interesting things that could be done with them. Yeah, I'd be happy to discuss any opportunities there might be.
We're also working on this characterization of natural fiber, especially rami. So we did this characterization from the single fiber until the bundle fiber. So yeah, we found quite large variability because when we made it into bundle and we tested, the strength reduces as compared to the single fiber, rami fiber.
So that happens with all fibers, even with carbon fibers. Then when you have a bundle, it's something I teach on our mechanics of composite failure. When you have a bundle of carbon fibers, the failure strain is always lower than the single fiber. And people find that quite surprising. You think, well, you've got a single carbon fiber and it's quite strong, and you put a bundle, you might expect actually it to be stronger because you've got a bundle, and when one fails, it's not catastrophic for the whole composite. But actually it doesn't work that way because of the variability of the fibers. And it's easy to think about it by thinking of a simple example. If you have a bundle of 2 fibers, then you load it up, one of the fibers is weaker than the other one. And when the weaker fiber breaks, it overloads the other one, they both break. So 2 fibers are always, if they're variable, 2 fibers will always have a lower failure stress than 1 fiber. And that principle extends to a bundle of fibers, and the bundle of carbon fibers has a much lower strength than the single fiber of carbon. That's where the role of the matrix comes in, because the role of the matrix is to limit the damage around a fiber break. So in a loose bundle of fibers, when one fiber breaks, that's it. It no longer contributes. But in a composite, it no longer contributes locally, but through the matrix, the load is reintroduced. And going past that critical length, the fiber is reloaded again. So what the main focus of the matrix intention is to reduce the effective length of the carbon. So carbon fibers and natural fibers as well reduce in strength as you get a longer fiber. Because if a longer fiber, you've got more chance of finding worse defect, which will cause the fiber to break. So a longer fiber is weaker than a shorter fiber. And by putting the matrix in there, you reduce the length over which those fibers can interact, and therefore you increase the strength. So if a single carbon fiber has a certain failure strain, you have a loose bundle, failure strain goes down. We put a matrix, it goes back up again. And the relative proportions depend on the variability and the strength of the fibers and the dimensions and the stresses, the yield strength of the matrix. So it's a very interesting, and with a good understanding of the mechanics, it's possible to try to design better materials. And that might be a very interesting thing to do with some of these natural fibers. And sometimes variability in fiber strength can be an advantage. So one of the things we found in this hyperduct program was actually that if you have more variability in the fiber strength, it actually leads to a more gradual failure. So there's trade-offs. Usually we seek low defects, higher strength, but sometimes to have more variability can actually be an advantage. And the critical question is to find how we can best use the characteristics of the materials we have to create something which is better for the particular application.
Thank you very much, Michael. We'd like to give opportunity for another 2 questions from the audience, and then they'll continue to the online participants. Maybe there are some questions from the online participants. Maybe 2 more, or you would like to? Okay.
Excuse. Good afternoon to Michael, Mr. Michael. First of all, I would like to ask about, since most of the presentation is regarding about mechanical properties, about the pseudo-ductile carbon fibers, I would like to ask regarding about the surface conditioning. So for the surface finishing or conditioning, does it also has influence on the overall mechanical behavior or damage response on the composite? Or for Mr. Michael stuff, it's not considered in this case? Thank you.
So you're talking about the surface conditioning of fibers when they're manufactured?
Yes.
Well, so that's an interesting question, and it takes me back to some research I did many years ago, where we had some work working with a carbon fiber manufacturer, and they produced carbon fibers with different levels of surface treatment. So this is another quite complex topic, and there's a lot of variable results in published papers. So I think it's not that well understood. What we found in that original, so we had fibers which had a standard surface treatment, and then we had fibers which were treated at less than that treatment and more than that treatment, and perhaps surprisingly we found that tensile strength was very similar for all of them. So there's very little difference in tensile strength with different levels of surface treatment. And that was perhaps initially surprising. What we did see was that the failures looked different. If you looked at the specimens after they'd been failed, the ones with the lower surface treatment had much more damage and more individual fiber failures, whereas the ones with a higher level of surface finish had a more brittle appearance. But the actual values in terms of failure strains were very similar. So my interpretation, so I would say the first thing is for tensile strength, it's not very sensitive generally to the surface condition. And generally the manufacturers know how to get a good surface condition and therefore get a good result. You obviously need a good interface. If you don't have a good interface, you can't get the load into the fibers, you won't get a good composite. But generally speaking, in carbon epoxy type composites, the interface in tension is not the weak level, not the weakest link. Now another example of that is in another part of this program, which I didn't talk about, when we were looking at discontinuous fibers, we were able to highly align discontinuous fibers and create composites with highly aligned but discontinuous fibers. And they gave quite good performance, almost as good as continuous fibers. But what that enabled us to do was to go through a recycling process. So we could load the composites, then we could burn off the matrix, and then make new composites from those recycled fibers and load them again. And what was to me quite surprising was that the tensile strength, after it had gone through several recycling phases, was pretty much the same. And that, despite the fact that during the recycling process, we'd used a fairly crude heat method. We just heated up and burned the epoxy off. At that point, got rid of any sizing of the fibers, and then we did not resize the fibers. We just put them back into epoxy and created another composite. And after one recycling, the strength and modulus were pretty much the same. After a few recycles, it did go down a bit, but not very much. And that was perhaps a bit of a surprise, because people talk a lot about the effect of size and how important the sizing is, as well as the surface treatment. In that case, it didn't make a huge difference. Now, that's not to say that this applies everywhere, because there's plenty of papers where people have shown that with varying either the surface treatment or the sizing, you can see sometimes some quite significant change in response. Probably more in compression than in tension, but you can. And also in other materials, so carbon and epoxy bond quite well generally, but if you take a thermoplastic material like polypropylene, then the bond is not so good. So in polypropylene materials, that may be maybe more of a problem than it is with epoxy. So in a polypropylene composite, getting a good bond is probably more challenging than it is with epoxy. So one of the things is it's difficult to generalize, and what happens with one material won't necessarily happen with another. So we have to be careful not to overgeneralize. Each material can be different, and we need to understand how the particular combinations behave.
Thank you, sir.
Okay, I think I would like to encourage the female student to ask, because we have also female students over here. So at least one of you, if you have any question, please. In mechanical engineering, we have this female student. It's constitute like 30% of our whole batch.
Well,
So
that's very good. I'm very pleased to see that. And we had quite a number of female researchers on this program, and 2 of them are now academic members of staff. Soraya Pimenta is now an associate professor at Imperial College, and Shun Wu is a lecturer currently at Southampton, but she's just about to move to a lectureship at Bristol. So it's always very nice to see success of any student, but particularly we don't have enough female researchers, and very pleased to see some more. So yeah, I'm very happy to take your questions and know what you're interested in.
Well, all right. Thank you for the opportunity. So I would like to ask a question. Previously on your slides, you showed us that this material is more likely to have a gradual failure, including fragmentations and also delaminations. And you've also shown us that in this research, you still like using the machine to like testing the compressions and tensions. And what I was wondering is, what if this material is using in the real cases for like maybe wings of aircraft, or maybe in wind turbines, that it has a cyclic loading. Are these materials still can hold it pseudo-ductile behavior, or maybe it would likely to be more, like faster the failure of it? Thank you.
So what we've been looking at here, and what I presented today, was all about the basic material behavior. And of course this will carry over into structures, and the critical question is, what is the design limitation in the particular application? So, and that depends on the individual cases. So taking the aircraft example, so we've been doing some more work on this. What I presented here was in this hyperduct program, but this work has continued, and we actually had, just a week ago, we had a review on the follow-on program from this one, where we've been looking specifically at compression, and we had somebody from Airbus at that meeting who was very interested in how this sort of concept could be applied on aircraft. And they were most interested in the notched compressive performance. So I showed here notch tension. In this program, we didn't do any work on notched compression, but since then, we have done some very recent work on looking at notch compression. And that is a design driver for aircraft. So because compressive response is usually lower than tension, and because you have many fasteners on an aircraft, many stress concentrators, they really like the idea of having an improvement in the notch compressive behavior. And in addition to that, in the compression, buckling is very important. So by adding high modulus carbon fibers to standard or intermediate modulus carbon fibers, potentially we can both improve the notch compressive performance, which is a design driver, and we can also increase the modulus, which is another design driver in terms of overall buckling. So for that application, Airbus thought that the notch compression is very interesting, and they wanted some further demonstrations of how this might apply, so that they could see whether it's something to take on board on their aircraft. Completely different application, Rolls-Royce, we're working on casings, and there, what's on a aero engine casing, the critical case is if a fan blade fails. So if a fan blade fails, which it's not supposed to, it's a requirement that the fan blade is designed that it doesn't fail, but if it does fail, it comes out, it should be contained by the casing. So there, they don't care about compression, but what they care about is ability to stop the fan blade, absorb the energy, and not fail in tension and bending. And there, the critical thing is how much energy can be absorbed. And we've found that these hybrid composites are quite attractive. So we've got a new program which just starting now, where we're going to be looking at some of these hybrid concepts to see if we can improve the penetration resistance of aircraft engine casings. So every application is different. We take a wind turbine, they are very sensitive to fatigue, and a lot of it is compression, because wind turbines are loaded in bending, so you have both tension and compression, but because compression is usually more critical than tension, compression fatigue is really an issue there. In that case, for pure fatigue response, we're not really improving it by this technology. So what we are doing is we're improving the overload capability. But if we're just considering the fatigue response for something which has not been overloaded, it's not particularly been improved. So maybe that's not the best application. But I think applications where you're worried about failure and you want non-catastrophic failure, such as well, I think the bicycle handlebar or bicycle frames is a good area, but you don't want a catastrophic failure. So that is a good application. So it really all depends on what the critical application is, which is different for every different product. Hope that's given some ideas about that. Thank you for the question.
Okay, thank you very much. So we continue to any question from the online participants.
Okay, thank you so much for your answer, Professor. So now I will be reading a couple of questions from our online audience. So the first question is, good afternoon, Professor. I am interested in how pseudo-ductile composites overcome the typically brittle failure behavior of conventional composites. In practical engineering application, what are currently the biggest challenges in designing pseudo-ductile composites that can achieve both high damage tolerance and manufacturability at an industrial scale?
So key challenges, I guess, the behavior is quite complex, as I think I've probably shown you this morning. There's a lot of design, even with ordinary composites, you've got a lot of design freedoms and a lot of variables that you can change. Now we're introducing a whole lot of new variables by being able to change the different materials, change the combination of materials, and so introducing potentially more complexity. And when we have, as I showed by looking at bending applications, we have different behavior in tension and compression. So it's quite tricky to optimize the design across all these parameters. And I guess in terms of industrial applications, tends to be quite a lot of conservatism, and trying out new ideas is always challenging. And so I guess the complexity and the challenges of trying new ideas are probably what holds things back. So we work a lot with aerospace, and aerospace are very conservative for good reason. I'm glad they are, because I flew here on a composite aircraft. So I think some of the applications may be more easy to obtain in areas where there's not quite such a key question about safety. So in sporting goods applications and other cases where we may be able to be a bit more bold in trying out new ideas. So I would say that the complexity of design and the overcoming the inertia and the risk with trying new things are probably what's the most critical things to overcome.
All right, so we'll be moving on to the next question, and maybe this will be the last question for our Q&A session for today. Okay, so this question is more about like your opinion as an expert in this field. So what is your future? What is the future application do you expect for pseudo-ductile composites?
Another tricky question here. I think these are very interesting materials. We have not yet actually got industrial applications of these materials. I think that's perhaps a little disappointing because the properties I think are really, really interesting. And so in terms of what the first application would be, well, I go back to the example we had with bicycles. We did have some discussion with several bicycle manufacturers, and quite a bit of interest was shown. We didn't actually get to the point where we implemented it in an actual structure, but I think there are possibilities in that field. I think the other area where I was expecting we would see early applications was in motorsport, because motorsport are very keen on getting really good properties, and also they have very quick turnaround times, and they're more willing to try things out. So we had several interesting discussions with motorsport Formula One teams, and that's an area where I thought we might get some applications. But to date, we've been mainly looking really at things in the laboratory, and we haven't yet got to the point of having industrial applications. So perhaps that's not a very good answer, but that's where we are at the moment. I also just mentioned earlier the applications we're looking at with Rolls-Royce on casings, so that might be another area where we might see some applications for this technology.
All right, thank you so much for the answer. As the time shows, we have come to an end for our Q&A section. So I would like to say thank you. Okay, so we would like to say thank you for Mr. Putu Suwarta and Professor Michael for a very insightful presentation and a very enriching discussion. Okay, there will be a couple of words from Mr. Putu Suwarta before we end our event for today.
So as we have learned from Professor Michael from these 3 days, so how many of you would like to study abroad, and after that you working abroad? So how many of you can raise your hand? How many of you would like to study abroad? Come on. See, so there are many enthusiastic students here who would like to pursue more knowledge and also to work abroad.
Well, as I mentioned on Thursday, we have master's programs in Bristol. We have PhD programs, and we'd be delighted to see some good students for those.
Yeah, hopefully we can do some collaboration with Bristol and ITS to do like a joint degree, some sort of that in a postgraduate level. So to summarize today's lectures, with this pseudo-ductile composite, we increase the damage tolerance of this wonderful material, as it is also lightweight, and we have a freedom to design this wonderful material. And with this pseudo-ductile behavior, we have the chance to increase its performance. It also hopefully it will be used in many industrial applications, hopefully in 2 and 3 years time. And and also we can also try to use this technology to our own benefit, for example, by using the natural fiber and combining it with synthetic fiber to increase those properties. So yeah, thank you very much, Professor Michael Wisnom, and please give a big applause to Professor Michael Wisnom. I will still be here until tomorrow, and if you would like to discuss with Professor Michael Wisnom, you're more than welcome. Is it? Yeah, you can discuss your paper or your work. Okay, thank you very much.
Okay, thank you very much, Professor Michael and Mr. Putu, for the very insightful presentation. So we are sure that all the audience here has gained a lot of new knowledge or even a new interest in composites material. So ladies and gentlemen, please give a round of applause one more time for Mr. Putu Suwarta and Professor Michael Robert Wisnom. Okay, so before we officially end our event for today, we would like to invite all the audience here to take a picture, Professor Michael and Mr. Putu. For our, so maybe for the audience, you can move to the center of.